Hello students. So we have left out with the last part of the module 3. Here, backwater curve and a flux. So what is this? Consider a flow over the dam. So here you can see the dam that is existing, and here there is upstream side and here there is downstream side. So the depth of water will be raising up to the depth of the dam. If there had not been any obstruction, that means if there is no any dam, then the path would have flow in the channel. The depth wouldn't be having constant, so it should be varied. So that's why, due to this obstruction, the water level rises. It has the maximum depth from the bed at some section. So at some section, the H1 will be the constant height. So here you can see the H1, the depth of water at the point where the water starts rising up, and H2 will be the maximum height of rising water from the bed. Then H2 minus H1 will be the difference in height. So this difference is nothing but the afflux. This afflux is defined as the maximum increase in water level due to the obstruction. So here you can see that is increase in water. H2 minus H1 will be the remaining height. This height is nothing but the afflux. The profile of water rising The profile of the rising water on the upstream side of the dam is called as backwater curve. So the profile you can see here, it is nothing but the water curve. So it goes on increasing as it reaches the dam. It is not that from somewhere it is coming and it is getting increased, but to a certain distance from the dam, it goes on increasing, and that height is nothing but the afflux, and the curve that forms is nothing but the backwater curve. The distance along the bed of the section is given. Water starts rising. Having the maximum height is known as length of backwater. So this length is nothing but the length of the backwater. So it is very easy to understand. So expression for the length of the backwater. So the diagrammatic remains almost same for the previous derivation that we have done. The energy line, v square of this height is v1 square by 2g. This height is h and z1. Here it is z2, v square upon 2g, and here is h. So again, when we get the datum height, the pressure head, the kinetic head, then again we need to make use of our Bernoulli's equation with bed slope and the energy line slope. So here you can see that is the Bernoulli's equation that is used here. Z1 plus H1 plus V1 square by 2g is equal to Z2 plus H2 is equal to H2 plus V2 square by 2g plus Hn. That is head loss that is going to take place. That head loss is nothing but the frictional losses. So we have seen there is two types of losses, that is major loss and minor loss. So that major loss is caused due to because of the friction, that is nothing but I into N. So Z2 is a 0, we are considering here. So substituting this Z2 in the equation here is 0. So I'm substituting HL value as IE into L here. So Z1 will be I, and Z1 will be IB into L. So therefore, the equation becomes IB into L into H1 V1 square by 2g, H2 V2 square by 2g plus I into L. So grouping again, so IB into L is on bringing on one side and IE into L bringing on one side, sending on the other the RHS side. So grouping it. So we will be getting L as a common term, IB and IE. Then this formula is nothing but the specific energy equation, that is H2 V2 square by 2g, H1 V1 square by 2g. So this formula indicates it is nothing but E2 and E1. So substituting this here, E2 and E1. So L will become E2 minus E1 by IB minus I. So this is the equation for the length of the backwater curve. Expression for length of the backwater curve. So here you can see one simple problem that is given here. By using some Manning's formula, we need to make use of it. So determine the length of backwater afflux of 2 meter in rectangular section, that the afflux height is given, and width is 40 meter and depth is 2.5. The slope of the bed is given, and the Manning's constant is also given. So V is given, that is H2 minus H1. So we need to be very careful here. It is height, h1 is given, h2 will become 2 plus 2.5, that is the remaining height. So ib and n is given. So calculate the a1, that is b into h1, and the wetted perimeter b plus 2h1. So hydraulic mean depth will be a upon b. Manning's formula. So previously we had used, that is Sedge's formula, c, so root mi, 1 by n, m raised to 2 by 3, I raised to 1 by 2. So substituting in these equations the values, all the values, so we will be getting 0.54 at section 1 velocity. So E1, calculating E1, and from this equation V1 square by 2g plus h1, from continuity equation V1 A1 is equal to V2 A2, calculating the V2 will be getting 0.3, and whereas the area will be calculating, that is B into H2, so it will be 180. So wetted perimeter is B plus 2 times of H2. So before we had calculated for first section, and now we are calculating it for the second section. So M2 again E2. So average of H is H1 plus H2 by 2, that is 3.5. V average is nothing but V1 A1 by A average. So that is nothing but H average we need to consider here. So it will be getting 0.3857. So MAV, that is hydraulic mean depth, is 2.94. So all the average if we take, so then substituting in the Manning's formula, so we will be finding out the values of bed slope, that is I, so 0.0003167. So length formula E2 minus E1 by IB into IE. So we have already found E2, E1, IB and IE. So substituting those values will be this length. So this is the length where the backwater curve that takes place. So this is about the backwater affluence. Thank you guys.